the next talk is brought to us by Thomas Weible and Dr. Gerhard Stein. And Thomas Weible is the creative brain of Flex Optics, a rebel who dreams of inventions such as the Flexbox. And Dr. Gerhard Stein is head of product development in Flex Optics, ensuring that innovative and amazing products can be announced to the market. And being on the forefront of optical industry, they will change gear today and talk about the market from an environmental point of view. Then, applause for Thomas and Gerhard.
Thank you very much.
Thank you very much, Melody. Yeah, it's great to be here back in Berlin. My name is Thomas Weible, co-founder and CTO at Flex Optics, and together with Gerhard, our lead research engineer, we want to show today something which is pretty new, actually. We are mainly in the field. What we do is in optical transmission, especially when it comes to the transceivers, and we provide there, or we build some tools to do some programming, but also now to do some analysis and measurement capabilities. And what we did is we developed in the last 2 years the Flexbox 5, and we use it now as a test equipment, and we're going to demo and show it here now what we tested. And that's the talk about how to analyze your network reliability up to 800 gig. And I'm just moving on now while Gerhard is still preparing. Is this my one?
I think we have to switch the HDMI connection.
Here we go. It's already switched. Perfect.
Great. Thank you.
I need this clicker here, not. So this talk is separated in 6 sections. Basically, I do a little bit of intro at the beginning. There will be something from last year. Don't worry, no exam again. From our last talk we did about coherent pluggables. And then we jump straight into the bit error rate dependencies. And then we move on with the temperature part and the distance part, what we figured out. This is quite a really hot topic, and then some takeaways. A little bit about the external tester, but as we are limited in time, we have to really shorten it down. We figured out we have way too much content, and we really want to be punctual today. So, yeah. So, this is a recap from last year, 2024. We did a talk about coherent optical transceivers, and there we introduced the SNR, the signal-to-noise ratio. And just a really quick recap is it's on the optical line typically, or the electrical, but now we are more focusing on the optical line. It's your desired signal to the noise level on the line. Okay, so now here we have a perfect SNR. You are quiet, I'm speaking, you hopefully understand me properly, and that's the ratio we can measure. This is more a point of view for the communication or the optical transmission guys, but now when you look as a network operator doing layer 2, layer 3, you are more interested in the bit error rate, which is actually you send out a stream of bits on the line, a certain pattern, and you receive it back, and you double check, hey, did I receive the same pattern which I sent out? And if there is a bit flip, for example, then you add to the counter 1, you have a bit error rate at the end of the day. Even more recap, back to 2019, I did a talk on 400 gigabit. So yes, 400 gigabit is already quite old. I introduced what is new on the 400 gigabit technology, and I pointed out in my talk 5 years ago, there is this digital signal processor thingy inside. And even last year, we showed what is doable with the DSP on the coherent part. And now we really want to focus on the analysis functions inside of the transceiver where the DSP is placed, and really look precisely on the bit error rate testing. So yes, there is a bit error rate tester inside, a pattern generator, and also a checker, and also the OSNR measurement. Beside that, the DSP does more in your network. It also does forward error correction. So it's not detection. It can detect errors for sure, but also can correct those errors later on. And finally, we made a lab setup. It's a really small one. We used the latest Flexbox now, which we have. We had to open it up a little bit because you will see later on it gets hot, quite hot. And yes, this is an 800 gigabit transceiver plugged into it, and but we will show a little bit more later on how the setup will look like. And yeah, we powered it up, and we used a couple of transceivers. So the devices on the test were 6 different transceivers starting from 100 gigabit, only focusing on single lambda ones, which do have a DSP inside. So the traditional old 4-lane transceivers don't have that DSP. And we moved on with the 400 gig. Yes, for sure, coherent need to be there as well. And 800 gig too. I pointed out the QSFP 112. This is a 400 gigabit new standard running 4 times 100 gigabit on the electrical traces. Pretty cool stuff. And when we come to the temperature testing, we only did it with 2 transceiver mainly because we went to the borders. We reached beyond the specs. We actually wanted to see what happens when we heat it up way too much. We took a coherent one and we took the 100 gigabit single lambda DR to do the extensive temperature testing and so on. And with that, I hand over to Gerhard.
Thank you very much, and yet again, welcome. We have taken out a couple of transceivers, as Thomas already mentioned. We cannot show everything, but you can download our slides. There's more information if you're interested in the curved discussion we are going to have. I will keep it short, promise, because I know some of us are already tired and waiting for the social. So let's take out the first transceiver, which is specified for 40 kilometers. It's an extended range transceiver, QSFP28, and connect a couple of drums together. So our measurement was up to 60 kilometers, which would be convenient, but I ran a couple of challenges, because if I tried to connect 2-meter cable, because I wanted to try it with different length, you have to attenuate these guys first, which would destroy our experimentation a little bit, but just a message to you, if you take a transceiver, you already might know that, and it's for extended range, longer range, you have to attenuate this properly. You can check this out in our shop as well, and here we have almost 8 dB and 3 dB difference, so you need a total attenuation of 11 dB. The Fibertron does that. You can calculate how much attenuation you have, but you might have to add more if you want to use shorter cables, and that is what I was doing, and it was my first measurement just to see what we measure with this device that was measuring the bit error rate. And yes, as you can see, the first 3 have 11 dB attenuation with 2-meter cables, 10 kilometer and 20 kilometer, basically, and it's very comparable, but after that, if I go beyond, I have to start removing attenuators. These are some clickable coupling elements. And what is mostly interesting, what I was targeting for, is 2.5 times 10 power by minus 4 that's specified for reliable Ethernet in the EEE 802.3 standard. So if you want to avoid flappy links, basically you try to get below this red section. Everything below is better. If you cross it, you have a problem. And as you can see with 50 kilometers, for example, which is at the edge, you can configure it a little bit with attenuators. Well, you get into this red area. So there is a correlation between temperature, but there are also other side effects which are very hard to explain, but if you want in a round later on, we can go deeper into this. We need to keep it a little bit short, but without any further ado, I'm handing back to Thomas with the next experiment. That was one transceiver. Now we are getting more exciting.
Okay, so then we moved on and used the coherent pluggable, and now you can see the little more details. We had to get rid of the housing of the Flexbox itself because it gets hot, very hot, when you don't place a heatsink on that. For sure, we need a fan, but even without heatsink, the fan was not sufficient to cool the coherent pluggable. And so that heatsink, actually, we got this from an old Cisco 800 router. A good friend of mine, he's somehow a wrecker. He tears down all type of networking and server gear, but what he really does, he really separates it precisely for pure material, and he has a whole stack of all kind of equipment, and yeah, it's a really interesting place there. He's around Frankfurt area, so if someone wants to get rid of his equipment, let me know, and he will take care. So yeah, we did the testing with the cooling first.
Yeah, with coherent, actually, it's quite interesting because, as you can see, I didn't have to use attenuators this time because you can do it with a low-power coherent transceiver. It's more expensive, yes, but quite interesting. We can also discuss this later. The 2-meter one is quite interesting. But other than that, we can see that the temperature doesn't affect that much the bit error rate. But the distance does affect it. So if I take longer fiber and connect them together, a couple of fiber drums combined and make my fiber longer, yeah, there's a jump. Now you might wonder, we have different bit error rates. Here we have a different specification. The IF range, we are within this range, so there's no red section, so we are all good. And yeah, basically that is what you get out with a coherent transceiver when you cool it. Now the challenge with this measurement device was that since it has a battery, it can last up to 10 minutes for these devices if you constantly cool it. That is quite a challenge. If you remove the cooling, it lasts for about 2 minutes, and unfortunately it's not the case. Now the 2-meter behaves a little bit more constant, and maybe you can think about, we don't need to discuss it right now, or maybe after this presentation, why now we have stable 2 meters and it doesn't bother. So coherent doesn't bother so much with a bit error rate. It's more precise in recovering, it's more precise in recognition, and with the FEC and with the DSP, and you can still use it without any attenuators. That's a big advantage because it uses lower powers anyways. So that is one thing. The other thing I want to show you, can I get played? Yeah. What happens, we don't want to destroy transceivers, but I have one here that has been, it is a little bit used, but still works. What happens if we get it above 85 degrees? I wanted to use a hairdryer or anything to blow really hot air into the transceiver, but as you know, convection is an effect that can also carry out heat, so it was really cooling the transceiver in the end. So I came up with an aluminium foil trick to just wrap it. There are more ways to do it, I know, but since this device also has a battery, you have to be careful. It's a little bit challenging to really get the transceiver hot, but keeps us a circuit cold. So I mean, we still want to measure something, right? But I was curious, since in your switch or when you read out your memory maps, you can read high warning and high alarm. I just put them there. And what happens if you go beyond? Because high alarm is like, oh, our transceiver is about to catch fire or smoke, anything. This did not happen at all. After 4 minutes, I already was in the high alarm, but I had to wait additionally 24 minutes to really get this degree. I went up to 86, but at this point where you see loss of signal, I didn't get any signal anymore. So that is what really happened with this transceiver. Was it destroyed? Was it broken? No, I just removed it. I put it back on. I left it cool down a little bit, put it back on. It continued working, and I was pretty impressed. I wouldn't have thought about it, but yeah. This is more interesting because the previous slide was OSNR. This is a bit error rate. It also becomes a little bit stable in the higher end, but it's still worse bit error rate, but it still works. I mean, the transceiver still was working up to 85 degree, 84 dot something, but yeah, it's something you should not do, but it's good to know that you still have certain margin window where you can move in. Another thing about the bit error rate you should keep in mind, whenever you read the bit error rate, you usually read average value, and since an average value, rolling average value also depends on the time. If you just leave it running, in many cases you have 1 and it goes down, or sometimes it starts with 0. It depends on the transceiver. So I wanted to really check if it's a time-dependent behavior we have here, because if the temperature rises and you have connected your transceiver, you also have running time, right? So it's counting, but it's at the same time it's heating. So I tried to separate this a bit and found out that after 4 minutes you really reach some stability. So you have 1.0 E-11, so still very low with a cable of 2 meters. I left this running for an hour, but after 4 minutes already it has the highest temperature peak, then it goes down and really stabilizes with a bit error rate. So if you wait for about 4 minutes, it becomes stable. That is what I did, and then I wanted to find out what what happens if a fan fails? Or, what I did in my experiment, remove the heatsink and the fan, what would happen? So, as you can see, we have this interesting curve with the temperature. Yeah, it goes up, but higher temperature also means higher heat transfer within your network gear. So this curve really explains it, but it's still a range, a section you don't want to have. And now I put the cooler back, my heatsink and my fan, and wanted to recover this bit error rate. And it did not happen. Can you see this? This curve still stayed 10 times worse. But the temperature properly recovered, and our signal also recovered, more or less. I mean, it's the same again, as you can see. So my question to you, any idea why the bit error rate did not recover to its original value? I have it here about where the 23 is close by. Can you see it? I'm not sure. The laser point's a bit weak. But it did not go down, not back down. Any idea what it could be? Good question. That's the thing. It's a rolling average. So in some cases, the firmware just takes the value, divides by 2. But other firmware, that is what I'm still trying to find out. How many samples does it take? Because on that it depends. It can recover. You can reset it. I mean, you can reset the whole transceiver, but you can also set certain bits to make it reset, and it goes back to the value. But it's something to keep in mind. Whenever you reach the bit error rate, it's always average value, a rolling average value. That's also another reason why this is a little bit more stable. I have not talked so much about the OSNR. I'll get into this, but now think of your favorite movie or video game and its main song, because I'm going to present you something amazing, something awesome, and I have to lift it up. Maybe Lion King, I don't know, I lift just this device up. That was my device for measuring all these values, and let me connect it for you. I'm going to explain this graph because we need to properly manage time. So what I'm going to do here is plug it in USB-C. Does it light on? Yep, it does. And yeah, we are already in the live demo, and I have prepared something for you. So Flexbox is here. Hoffentlich kein Vorführungseffekt. How does you say this in English? I have no idea. And let's connect the transceiver here. So let's plug this guy in. Click, it feels good. So let's wait a bit. This guy needs to boot up. The DSP needs to boot up. So let's give it a couple of seconds of time. And let me tell you what I just did here. So we have a 2-meter jumper cable. You just saw a QSFP transceiver and a Flexbox 5. You can see it here. So for the audience that is in front. And my Python setup. My Python setup is a prototype for the application what we want to publish next year. So I'm still doing some experiments here. And I hope it's ready. No, it's not ready. It's still booting up here. Takes a little bit of time. It's executing the PRBS generator on the line, which is basically responsible for generating the bit stream. So your DSP on one side generates the bits, pushes them over the line, and on the other side it starts verifying this. And cable doesn't like this so much. And here we go. Live monitoring of bit error rate. So it's the first time you're seeing this with our device. And as you can see, temperature goes up. I'm not cooling this device, obviously. Bit error rate goes up because it just started measuring. So it's a little bit flaky here, but it should stabilize a little bit. Depends what you do with the cable, I guess. Maybe, well, with 10 by -12, it's a little bit more sensitive, usually. And you have OSNR. And as you see with the OSNR, it is jumping a little bit. The thing is, in your specification of SIMS for the transceivers, you have these jumps because that's the way how it's resolving it. If you have a value measured between 23.6 and 23.4, like 23.5, it starts jumping because it has to decide between a value. But after some time, as you can see, it stabilizes. Sometimes I have this oscillation later, sometimes earlier. It depends on the condition, how well you cleaned your connector and all this stuff. So yeah, this would be running for a couple of seconds. I think it goes up to 300. You don't have to wait the whole time. I put it for 300 seconds, basically in a very safe window. But I also added some control circuits that controls the temperature because, you know, 70 degrees is something you don't want. A warning usually starts with the transceiver 73, but let's keep this cool. But as you can see, the higher the temperature, the higher the bit error rate, something you don't want. So also cool down your devices. At least the signal is stable, and the bit error in this case a little bit stable. No hairdryer, it's all good, I would say. Yeah. That is my little live demonstration. This was with 2 meters cable, but obviously we can show more here. Because I also tested this with longer fiber, but I didn't bring here the drum. That's the wrong slide. Excuse me. My apologies. Where were we? Yeah. So with 10 kilometers, I made the same measurements. You can see we have these oscillations I already talked about. And as you can see, we have usually an OSNR, which is between 20 and 30. That is quite normal. If it's below 20, it's not so good anymore. 30 is might be good, but usually what I have observed, it's below 30 what we usually measure. I mean, it makes sense. If you have a very high OSNR, you might be wasting energy as well. You need a signal. That is important. It should be a good enough signal, a signal you can recover, and that is fine for the transceivers. And as you can see, there's a relationship between temperature and bit error rate this time, because that is not a coherent transceiver, this is a direct detection transceiver. And what we have here are 2 dimensions. So for distance and for temperature, what we get here, you don't want to get into the red section, stay in the blue section. If you want to use this transceiver, it is specified for 500 meters, but it still works on 10 kilometers. Up to 20, you have a signal, but please cool it down. If you don't cool it down enough, the bit error rate is getting worse. So, yes, almost. Thank you very much. Now, some takeaways for you. I tried to make some nice Chinese box takeaway, and with Flux AI and the Hugging Face generated me this one, but for some summary and takeaway, what is interesting, what we have been researching, investigating, the bit error rate on the direct detection transceiver, non-coherent transceiver, depend on both temperature and fiber length. And we have a rolling average. You should always consider that. And yeah, maybe a third thing, now we can measure this. And if I put transceiver into a gift box, I get this one. And Thomas, you explain the rest of our takeaways.
Yeah, so I think the rolling average is also a really important value to know when it comes to error counters on your networking device. So when it is the capability there, and I'm not aware if some of our network operating systems already have BER functions in their operating system implemented, because it is actually done by the transceiver, the BER, and you only need to access it via the management interface. That's what we did now also with the Flexbox. And when you for example, have an issue, what Gerhard also showed, is like if you have a temperature problem and the BER, for example, while your testing goes up, you really need to take care that the counters are resetted afterwards, because otherwise you get somehow false values, or you have to wait a longer period of time to get in a proper range again, because it's a rolling average. What we have seen as well is also in the coherent ones, what we also showed last time, the DSP does way more functionality inside to get the properties of the light beside the amplitude, but also the phase and the polarization sorted. And it also has more features just due to the fact that it is these more properties of the light to recover the signal than compared with a direct detection transceiver in this circumstance. This means also the coherent transceiver is a little bit more, let's say, ruggedized. It mainly relies on the fiber length, but not so much on the temperature changes. For sure, when you overheat it, then it has a serious issue, but not on the changes. That's what we saw. And then, in general, when you run your network, it's also helpful to know where are my boundaries. So look in the standards, and for example, the IEEE on the Ethernet for 100 up to 800 gigabit defines the maximum bit error rate you can have coming up from layer 1 without having interruption on layer 2 in turning out in CRC errors or even worse, flapping links. So when you know those figures, and Gerhard showed them, 2.4 to the power of -4, which is actually an okay-ish bit error rate, you still can operate your layer 2 and above with a proper service on those high-speed links. And just the final one is outcome also for us when we saw the measurement which we did with all the different 6 types for the direct detection transceivers, so mainly for the gray ones. The BER is actually, when this is fine, you don't need to take care about OSNR at all. That's quite helpful, because then you only have to look at one value. This brings us to the end of the presentation, and yes, we are very happy that we showed it to you today, what we did there. This research, actually, what Gerhard did here now with the BER function is currently lab environment, but with the goal that we get it ready to our software next year. That's the goal, to have it public available. I can't promise when it will be there. We still have some challenges to get now the final release done, which is actually this week. It was luckily, together with DENOG, get Flexbox 5 online. With that, thank you very much for having us here, and for sure we are taking questions.
Thank you, Thomas and Gerhard.
Thank you.
Are there any questions from the audience or the internet?
1, 2. So. Thank you for this talk. Question: did you find out how big this rolling window is? Is it seconds? Is it minutes, hours, days, or since power up? Or is it configurable or documented?
I'm pretty sure it is since power up, at least. Because usually you read, when you have the chance to read a value, either it's 1 or it's really a perfect 0, which doesn't make sense. It just has started, obviously, and then you read out values. Unfortunately, I don't know what window is being used, but I could imagine, because, I mean, the DSP has a firmware, the easiest way to do this is just read out the memory and print it out, but I'm not sure. We need to research this for our production line, and I will ask this question. I really want to know.
But then this would mean that it never resets to 0 again if it's from power up, right?
Yep. Because typically the idea of this BER function is that you don't run it forever. It's not a fully, let's say, network tester. It is for a short period of time to see if it's properly set up, because the main goal of the transceiver is to build your link and not to do testing.
You also have a little bit of control. You can set certain bit. You don't have to pull out the transceiver, put it back in, and take away the power. There are bits you can set, so it resets the counter back again. So there's something you can control about it, but how really it measures the window, we need to look deeper into this. We just started measuring these values.
Hi, Nicolas Korten, Comro GmbH.
Oh.
Here. Can you explain what happens at the transceiver when, by increasing the temperature, you reach a point where the bit error rate gets much lower? What happens there?
Actually, these DSPs, to my understanding, what I have read in the documentation, have some control circuits. I could imagine that it does some controls of power, but I don't have really deeper insights into it. But we can look together if you're interested to see more of these. Yeah, I mean, new answers, new questions, I know. We just scratched the surface there.
Yeah, it looks interesting to me. Okay.
Yeah, this big diagram with the jumps and all this, yeah.
Right. Okay, thank you.
Welcome.
Any further questions? I think there are no further questions, so thank you.
Thank you very much, Melody.
Thank you.